Oh yeah, I would be really
Hi everyone, welcome to the second class talk in our summer Colloquium series. I'm Jenny.
And I'm Taylor.
And today our speaker is Dr. Laura Brenneman. Dr. Brenneman received her undergraduate degree in astrophysics in 1999 from Williams College, and then she went on to receive her PhD from the University of Maryland in 2007, studying black holes and AGN. She did a postdoc at NASA Goddard Space Flight Center for 2 years, and then she came here as a postdoc working with Dr. Martin Ellis until 2014, and now currently she is Smithsonian staff. Today she's going to tell us about her research in black holes. So without further ado, welcome Dr. Brenneman.
Thank you guys. I think everyone can hear me, hopefully. It sounds like the microphone is now on. That's always a good start. Well, thank you very much. I was just saying that I don't often get the opportunity to talk to a mainly undergraduate audience, and it's actually a real pleasure to kind of take a step back occasionally from some of the minutiae that you get involved in every day and think about the big picture of the research that you do. So thank you very much for the opportunity. I appreciate it. So as the very nice introduction just said, I'm going to talk to you guys a little bit today about the research that I mainly focus on, which is studying supermassive black holes in active galaxies, specifically in high-energy X-ray emission. I'm going to start off by giving you kind of a brief introduction about supermassive and massive black holes and active galactic nuclei, so-called AGN. I'm going to then move on to talking about how we probe the innermost environments of these AGN through X-rays, specifically X-ray spectroscopy. I'm going to touch on broad iron lines, particularly as diagnostics of the innermost accretion disk and the accretion flow. And then I'm going to move on to the larger topic of constraining how fast black holes in AGN actually spin or rotate. I'll talk about the implications of these spins for AGN evolution and feedback, and then I'll leave you with some takeaway points and some hints at future work in this field. So I'm sure just about all of you have seen this image. In fact, for most of you in the audience, you were probably very young when you first saw this image. This is the so-called Hubble Ultra Deep Field, and one of the most amazing things I think about this is that nearly every single point of light in that image is a distant galaxy. And we now know that almost all of these distant galaxies contain supermassive black holes at their cores that have been intimately involved in the galaxy's formation and evolution. But of course, one of the great questions in astrophysics is the sort of chicken and egg argument, which came first, the black hole or the galaxy, and how exactly have they, or indeed have they, influenced each other over cosmic time? Well, we think the answer to that question is a resounding yes, based on the plot that we see here on the right, known as the so-called M-sigma relation. It was first put forward in about the year 2000, I believe, by Ferraresi and Merritt, and has since been reincarnated several times through many different studies. Basically, this describes a relation between the mass of the supermassive black hole at a galaxy's core and properties such as the stellar velocity dispersion, or how fast stars are buzzing around in that galaxy. And it turns out that there is a very tight correlation between those two values over several orders of magnitude in black hole mass. This is interesting because when you consider the gravitational sphere of influence of a black hole, even a supermassive black hole, what we're talking about is something that's effectively of order the size of our solar system. And it seems to have intimate knowledge about things that are happening on the scales of distances of galaxies, which are of order, of course, many kiloparsecs. So the question is, how does something that is effectively like the size of a grain of sand in Kansas affecting things in Los Angeles or New York. That's the type of scale that we're talking about here. So we know it's not gravity. I just told you about the size relatively of the sphere of influence of the black hole's gravity relative to the galaxy as a whole. So the big question, of course, is how does this relation come to be? For those of you that were at Brian McNamara's talk yesterday, I think you've gotten a preview of this answer already, a pretty good one. The plot on the left is something I directly stole from his talk, in fact, and this basically describes the relation between the spatial density of galaxies and the brightness that we see of their stellar distribution. And if you were just to assume the galaxies form by collapse of some cooling cold dark matter model halo, you would see the relation that's shown here in the blue line. What we actually see is the relation described by the data points here, where on the right it seems like we have a decrement of galaxies at the very bright end, and that seems to be governed, we think, suppressed star formation here by feedback from the AGN, and then at the lower end of this distribution, perhaps by feedback from stellar winds. So I'll touch more on what we mean by feedback later in the talk, but that's just a preview of what's to come here. Black holes, by their nature, are some of the simplest objects in the universe. They are astrophysically oriented around two main properties, mass and spin, and that's it. Technically, you could also have a charged black hole, at least theoretically, but if you were to place a charged black hole in an astrophysical environment, it would very quickly accrete particles of the opposite charge and neutralize itself. So mass and spin are basically the two properties that govern a black hole. Now, I'm sure a lot of you have seen in your physics classes or your astronomy classes the demonstration of placing a bowling ball on a trampoline or something to that effect. We know that mass deforms the space-time in which it resides. So the mass of a black hole effectively creates a potential here, a potential well in the space-time in which it resides. It warps the space in it, and that means that lines or photons that are traveling nearby have to go on curved geodesic trajectories if they cannot move in a straight line near a black hole. Spin is a little bit more of a complicated issue, and it manifests much closer to the black hole than does mass. I mean, to figure out a black hole's mass, it's essentially a two-body problem. As long as you have something orbiting that black hole that has mass, you can figure out how massive the black hole itself is. Spin, as I said, a much more subtle effect, and it manifests very close to the event horizon, so on tiny scales, relatively speaking. Spin induces a phenomenon known as frame dragging in the space-time around the black hole. So basically, if you spin a black hole, if you rotate it about some axis, it forces the space-time in which it resides to kind of co-rotate with it. It's kind of like moving beaters through a thick batter, if you've ever made a cake or something like that. Literally, the space-time is forced to co-rotate with that black hole. The reason we think spin is interesting is that in two different classes of black holes, in stellar mass black holes and in supermassive black holes, you have different kind of arguments for why spin is important. So it's thought that in stellar mass black holes, for reasons I don't have time to go into, the spin is chiefly natal. This is the spin that the black hole was probably born with, or something close to it. So in this case, the spin of a black hole can help us probe the formation event, say the supernova explosion that created that black hole. In the case of an AGN and a supermassive black hole residing at its core, these are masses that are typically millions or even billions of times that of our sun. And we think that these have built up over cosmic time by a combination of accretion of gas nearby and also mergers with other black holes. So the question is, how much of a role, relatively, did accretion versus mergers play in the buildup of the black hole? And it turns out, as I'll get to later in the talk, that spin can tell us about that distribution. Finally, we think that spin actually helps drive jet production and outflows in black holes, which then seed the interstellar intergalactic medium with matter and energy, possibly suppressing star formation and helping fuel that feedback process that I mentioned earlier in the talk. So in terms of how we go about measuring spin in black holes, we use a method called interdisk reflection modeling. It turns out that for stellar mass black holes, the small guys that formed from stars about, say, 20 or 30 times the mass of our sun when they were on the main sequence, you can also use a different method called thermal continuum fitting. And there are people here, such as Ramesh Narayan and Jeff McClintock, who are very expert in that method. I'm not going to touch on that too much today because it seems like, for various reasons, that is more reliable for stellar mass black hole spin estimation than it is for supermassive black holes. You can also use, in theory, 4 other methods that I describe here: QPOs, or quasi-periodic oscillations, iron K reverberation lags, orbiting disk hotspots, polarization degree and angle versus energy plots, And actually, you can image now, or very soon, the inner disk and event horizon through millimeter wave VLBI imaging, the so-called Event Horizon Telescope that you may have heard of, touted in the news recently. Of course, you can only do that for two sources, unfortunately. The Sagittarius star, the black hole at the center of our galaxy, and M87 need to be relatively large, spatially speaking, in order for us to use that method to image them. All of these methods are, in theory, able to tell us about the black hole's spin, but for various reasons, either we don't have a polarimeter that's sensitive in X-rays that's orbiting the Earth right now for polarimetry, or we just don't have the technological capability or the theoretical understanding yet to truly apply them. So the method that we're left with, highlighted in red, is inner disk reflection modeling. The way this works is we know that AGN exhibit a so-called reflection spectrum. So when you're talking about the innermost part of an AGN, and I apologize, the contrast in this is not fantastic, we think that if you look edge-on at the system, so here's the accretion disk, here's the black hole at the core, there exists some reservoir of relativistic electrons, either a skin on top of the accretion disk or maybe in some sort of spherical geometry around the innermost portion of the disk. In any case, some as yet unknown geometry. But we know that these electrons exist because when we look at these AGN and X-rays, the spectrum that we see is dominated by a power law. And that power law, which is shown in the plot below here as the hashed line, is the direct result of a Compton scattering process. So the accretion disk, kind of like a stove, radiates thermally. It's just really, really hot. So it radiates thermally in ultraviolet radiation for an AGN. If we're talking about a stellar mass black hole, it's actually so hot that it radiates in X-rays. But for the AGN, you've got ultraviolet photons that then go up and interact with these relativistic, fast-moving electrons via Compton scattering. And that process naturally produces the radiation that we see coming to our eyes or to our telescopes in the form of a power law. Those are the photons that are scattered away by the electrons, getting a boost in energy and becoming X-rays. There are also photons that scatter off the electrons and get a boost in energy and become X-rays, but instead of coming to our telescopes, they get reflected back down onto the surface of the accretion disk. And it turns out that when that happens, the disk, which is now being irradiated with X-ray photons, is seen as relatively cold. And so you get this fluorescent emission line spectrum that gets produced with all these lines of various species getting fluoresced in the process, along with this sort of hump over here, this Compton backscattered continuum. So what you see from the reflection off of the disk of those X-ray photons is this series of fluorescent X-ray emission lines. And the one that turns out to be the most prominent here is the iron K line, due to its high energy, its relative abundance in the system, and also, most importantly, its very high fluorescence yield. So, connecting this to black hole spin, it turns out that the structure of the innermost accretion disk changes depending on the spin of the black hole. As you increase the spin in a prograde direction, so if the black hole and the accretion disk are spinning in the same direction, it turns out that frame dragging, as we discussed earlier, can rotationally support orbits in the disk that are much closer to the event horizon of the black hole than if the black hole is not rotating. So it turns out that this innermost stable circular orbit, or the ISCO, in the disk changes depending on the black hole spin. So for a non-rotating black hole, as seen in the center, non-rotating in this case for a dimensionless quantity, we call the spin of the black hole A, and we say it's 0 if it's not rotating. The ISCO is set by general relativity at 6 gravitational radii, which is a unit known as gm over c squared, just a unit that's convenient for us to use on spatial scales like this. As I said, if you spin up the black hole, the frame dragging rotationally supports lower orbits, and so you're able to pull in the inner edge of the disk, or the ISCO, down to nearly 1 gravitational radius. Now, you might think this is a little bit strange, but in certain situations, it might be possible to have a retrograde configuration between the black hole and the disk, in which they're spinning in opposite directions. In that case, frame dragging actually works in reverse and pushes your innermost stable circular orbit out, because it forces these orbits to fall off more quickly and plunge into the black hole. So in this case, your ISCO is at 9 gravitational radii. So depending on the spin of the black hole, the innermost stable circular orbit changes, and this is shown mathematically by this plot. RMS is just another way of denoting the radius of the innermost stable circular orbit. So the black line is the radius of the event horizon, changing depending on the black hole's spin. And here is the very nice monotonic relationship between the ISCO and the spin of the black hole. So for each value of your radius of the ISCO, there's a unique value of black hole spin associated with that, which is predictive. To illustrate exactly how this works, imagine that you have a disk that's made up of a series of rings, or annuli. And let's start with a ring that's at about 400 gravitational radii, or gm over c squared, away from the black hole. For context, this is pretty far. Turns out that the line profile you would get if this is just a disk made up entirely of iron atoms is this nice little Doppler-broadened double-peaked line. Purely Doppler shifts are playing into the shape of this line. The reason you have two peaks is because the disk is rotating, and if it's angled toward your line of sight, you have one part that's coming towards you and one part that's going away from you. So you have a relative red-shifted and blue-shifted component of that line profile. Moving in closer, you start to see that there's a characteristic asymmetry that's beginning to come into play here. So this is a factor of 4 closer to the black hole. You can see that that line is broadened and also slightly skewed with respect to the previous line. Moving in further, you see that that effect is enhanced. This is special relativity. So in this case, we're talking about beaming coming into play. The blue wing of the line, the one that's at higher energy, is coming towards us and is boosted not only in energy but in flux. Similarly, the red wing is kind of deprecated, not only in energy but in flux. Moving in closer still, you see that this effect starts to now manifest in terms of dragging the entire line center down to lower energies. And as you move in as close as you can get for a non-spinning black hole, the effect is magnified even more. So in this case, the dragging of the line down to lower energies is general relativity kicking in. This is the gravitational redshift that you've probably all heard about in your physics classes. So when you combine the Doppler effect, special relativity, and general relativity, and you add up all of these rings in the accretion disk, you get a profile kind of like the one shown in black here, where it turns out that the red wing is very, very sensitive to the location of the innermost stable circular orbit in the disk, and the blue wing is very sensitive to the inclination angle of the disk to our line of sight. So you basically just added up all the emission from all of these rings, integrated over all of them, and you see this sort of broadened, skewed profile. And again, this is for a non-spinning black hole. So even a black hole with no net rotation shows this odd spectral profile. Very different from when you take a spectrum, like in a class or something, you're pointed at a hydrogen tube, and you look at a hydrogen line, and it's this teeny little delta shift. Not so in the environments near a black hole. It turns out that these broad iron lines are very prevalently seen. They're seen in a lot of different AGN. Here's an example from a colleague of mine, Paul Mandra, who wrote a very nice review of this in 2007. They're also seen in stellar mass black holes. This is another colleague of mine, John Miller. He's done a lot of work in this area. And they're even seen in neutron stars. So you don't even need to be a black hole to have a broad iron line. Anything that is actively accreting, any astrophysical source that is powered by accretion onto a compact object is going to show these features. It's expected. So now, back to this picture. Broad iron lines are only part of the story. Recall that I referenced an entire reflection spectrum, of which iron was the most prominent line, but there are a whole sea of other lines and this Compton hump here that we have to keep in mind. And it turns out that there's been some really interesting work that's been done on this in the past decade. Some colleagues of mine have been working very hard on developing models of what a static, so-called static disk spectrum looks like. So if you were just to irradiate a slab of material, no black hole anywhere in sight, with X-rays, you would get the spectrum that's seen in black. Here's your iron line, here's your Compton hump, and here are all the lines of all of these other elements down here at lower energies. But when you embed that in the gravitational potential that's caused by the presence of the black hole at the center of the disk, what you really see is the profile in red here. So it changes things quite a bit. This iron line gets broadened and skewed, as we saw from the illustration in the previous slide. But then down here, it really smooths out a lot of these very sharp emission features as well. And it turns out that when you look at a real AGN spectrum in X-rays, very often you'll just sort of see a hump down here. We call it the soft excess. And it turns out that this relativistic emission from this reflection spectrum could play an important role in these soft excesses in AGN. But anyway, the areas to focus on for the remainder of this talk are the higher energy portions here, the broad iron line and the Compton hump. Oops. So when we're talking about connecting the structure of the accretion disk with its actual appearance spectroscopically, what we're talking about is something that matches up kind of like this. So for a non-rotating black hole, you see your iron line, you see your Compton hump. For a fast prograde rotator, you get a lot of gravitational distortion here on the soft end, and it actually changes your Compton hump a bit too. And then in the case of a retrograde rotator, your line is a lot narrower, and a lot more flux is kind of centered around the 6.4 keV rest energy of that line. Now, the complicating factors are that we don't really observe AGN as very clean systems. There's a lot of stuff in the way. There's gas, there's dust. I mean, recall that these black holes are at the centers of very massive galaxies usually, and very active galaxies. So they're producing huge amounts of radiation, some of which comes out as jets, as you see here in this Hubble Space Telescope image. But if you zoom in on the centralmost portions of these AGN, very often you'll see this sort of donut-shaped structure at the core. This is just one example of many that you can point to. And if you were to draw a schematic of what this actually looks like, we think that there's sort of a toroidal reprocessor, the so-called torus, in a lot of these AGN, that impacts how we view them, depending on at what line of sight we see this whole structure. But if you were to zoom in farther, down to the core of the system, you would see the black hole, the disk, and this so-called corona of electrons that we see around there. So this is just to give you a feel of scale. But there are a lot of different components that go into an AGN, and as a result, there are a lot of different signatures that come out of them in X-rays. So we're not just seeing the reflection spectrum cleanly, we're seeing the power law continuum, we're seeing the Compton hump and the iron K edge both from the torus, this distant reflection, as well as from the inner disk, very close to the black hole, from the accretion disk. Sometimes we're seeing jet emission, this is a radio loud source, and very often we're also seeing something called warm absorption. So these systems have prodigious amounts of outflows, winds, that tend to fly off of the accretion disk. And it turns out that, ironically, the more they accrete, the more they throw off. So very often the brightest systems have very strong warm absorbers associated with them as well. We think about 50% of all AGN at least show these characteristics of absorption. But in any case, all this gas that's sitting there in the way complicates our view of the reflection spectrum. And as a result, when you want to study these spectral features, you really have to pay close attention to how you separate out the reflection spectrum from all of these other components. And the superposition of these features in the spectrum really necessitates that we have a huge amount of photons, just enormous photon statistics, in order to aid us in separating these features and isolating the reflection spectrum. So I'll focus primarily on this issue of the complex absorption in AGN. I already referenced warm absorbers, these sort of outflowing winds that we tend to see from the accretion disk. But there's also cold absorption from a variety of different radii in the system. There's cold absorption from the torus as well as reflection. Sometimes systems even display variable absorption, as with clouds passing across our line of sight. I'll show you an interesting example of that in a minute. But considering all the different layers of gas that are in our way along the line of sight to the black hole and the corona and the innermost part of the disk, it turns out that the hardest part of figuring out black hole spins is separating out all these different bits. So looking at this is just kind of a schematic of how absorption can influence what you're seeing. So here on the right is just a prograde rotating, fast rotating black hole. You can see the sort of canonical feature with the iron line and the Compton hump, where you have the gravitational distortion here on the red end and this sort of high energy excess of the Compton hump. But what if you were to take a spectrum like this and you were to put all these clouds in the way, these absorbing cloud structures? What would the spectrum look like then? Well, it turns out that at least to first order, it would look a lot like this, actually. There would be this sort of dip here, this absorption feature, and that would kind of mimic the features that we see up here in the case of gravitational distortion. So in the case where you have both of these effects happening at the same time, some sort of black hole rotation you're trying to measure, and a lot of clouds in the way from absorbing material, you have to be very careful in terms of how you separate these things out. One of the best examples of how we use X-ray spectroscopy to separate out all these different components is the AGN NGC 1365. This is work that a colleague of mine, Guido Rizzoliti, did a couple of years ago and was a Nature paper, so very, very highly touted in the community. And one of the things I'd like to show you here is the black line versus the red line. The black line is a model that has both a rapidly rotating black hole as well as some warm absorption in the spectrum. The red line is a model that just takes 5 different layers of warm absorption and has no spinning black hole at the middle. Just the absorbers are the red line. When you look at the green data, which are taken with XMM Newton, and you don't have any access to energies above 10 keV here. You're just looking at the green data. Those two models basically lie on top of each other. They're effectively degenerate. We can't tell them apart. But when you extend those models out into higher energies, and then you plot the new star spectrum on top of them, in the blue data points there, you see that it very closely resembles the relativistic reflection model that does contain absorption. It does not at all resemble the model that only contains absorption and no relativistic reflection. So new star has really pioneered kind of the next era of black hole spin measurements. And this kind of confirmed to us something that we already knew, but that really was brought home. We really need broadband X-ray spectra of high sensitivity in order to do this work. If we restrict ourselves to just Chandra, just XMM, or just Suzaku, those are three of the most prominent X-ray telescopes that we have access to these days, we're missing half the story. And that half the story that happens at high energies really probes the shape of the Compton hump and can tell us about whether reflection or absorption is the correct model to be using for these sources. Now, it turns out that this particular source does have sort of orbiting clouds along the line of sight that do a lot of absorbing. And it turns out that the level of absorption changes. So over the course of about a year, New Star and XMM together observed this one galaxy 4 different times. And you can see it ranged over about a factor of 100 in the thickness, the column density of that absorbing gas. So quite a variation. This is an unusually large amount of variation in an absorber. So interestingly, when you factor out the absorption, and when you factor out the power law continuum that we know is there in all AGN, you see residual features that look almost identical between those 4 different observations. And that's reassuring, because that tells us that what we're doing is probably right. The underlying features of relativistic reflection here are expected to be seen, again, in any actively accreting source onto a compact object. And that seems to be exactly what we're seeing here, underlying all of the absorption. It turns out that when you measure the spin in this galaxy, and you do it 4 different times for each of those different observations, it gives you the same answer. This, again, this is a zoom in up here of kind of the highest end of the fast rotating prograde spins. Turns out that this is a very rapidly rotating black hole. And even though there's a prodigious amount of gas in the way, and this gas varies on time scales as short as a few months or even a few weeks for this source, it doesn't matter. Using the modeling that we've done here, we're able to correctly measure the black hole spin and reproduce that result, even for column density changes by a factor of 2 orders of magnitude. So this is very impressive work. And then on the left here, kind of again confirming what we're seeing, is that if you treat the iron line and the Compton hump as 2 completely distinct features that have nothing to do with each other, you would expect that if they were part of the same process, they would vary the same way. So it would be really disconcerting, for example, if we were to measure the strength of the Compton hump and measure the strength of the iron line during all of these different observations, and they came out to have nothing to do with each other. There was no relation between them. That would tell us that maybe our models aren't right, because if these things are truly coming from the same physical process, reflection, they should have everything to do with each other, and in fact they do. This is work by another colleague of mine, Dom Walton, on NGC 1365. So why do we care, ultimately? Well, like I said, it turns out that in AGN and supermassive black holes they contain, we can figure out a lot about the relative roles of mergers of multiple black holes, and gas accretion over cosmic time by looking at their black hole spins. And especially when you get a distribution of spins, like hundreds or even thousands of spins, you can start really talking about trends statistically in what we expect. And it turns out that some numerical simulations done by Marta Voluntari and Emanuele Berti several years ago were very telling in this way. So on the left, we see what happens when you only grow black holes over cosmic time by merging them with other black holes. Turns out that your spin distribution is fairly flat. It's kind of all over the place. When you grow the black holes via mergers and what's known as chaotic accretion, so if you accreted gas from all different angles, all different angular momenta, it turns out that you spin down the black holes. You wind up with this population of relatively low spinners over cosmic time. But if you grow them with mergers and prolonged prograde accretion, turns out that you get a population of very rapidly spinning black holes over cosmic time. And this is over several different bins in redshift, showing you what you would expect. This is basically like taking a basketball and spinning it on your finger. And prograde accretion basically means that you're throwing more gas onto it, more momentum in the same direction all the time. So you're just spinning it faster and faster and faster. So, mergers of galaxies and eventually their black holes can result in a wide range of spins, but if we can get enough spins and a great enough sample of AGN, we can test this. Here's how we're doing so far. So these are all the spins that have been pulled from the literature. My work, a lot of other people's work have gone into this. And you can see it's still a relatively small sample size. We have about, I think, 25 spins that we've measured in individual galaxies. And then the red spot up here is a sample of 27 lensed quasars from Chandra. And it turns out that when you stack their spectra, the average spin that you get is about 0.7. So these are too far away for us to get good enough photon statistics to individually measure the spin in each galaxy. But when you stack up all their spectra, the average is still fairly high. So what we're seeing so far is very interesting, but we have to keep in mind a couple caveats. First of all, this is still a very small sample size. Second of all, we're probably thinking of selection biases here. I mean, by nature, as I said to you at the beginning of the talk, this type of science requires a lot of photons. In order to get a lot of photons, you have to leave your camera pointing at this object with the lens open, the shutter open rather, for a long time. We're talking about hundreds of kiloseconds, which translates to several days at a time for a galaxy. So this is not like going off to the Keck telescope and integrating for an hour and having your beautiful optical spectrum. This is much more photon intensive. So it turns out that it's pretty hard to do this. And the other thing about X-ray astronomy, of course, is that since our atmosphere is opaque to X-rays, all of our instruments are in space. This means that you can't just go to the observatory and kind of do things. You have to apply for telescope time. And there's a group of people that looks over your proposal and says whether they want to do it or not, basically. So you have to bid against a lot of people. Telescope time is usually very oversubscribed. So even getting these observations is very challenging, not to mention doing all the data analysis that goes into measuring the spin. So a couple caveats to keep in mind. That said, maybe we're starting to see a little bit of a trend between spin and mass. Maybe. Turns out that as you go to higher black hole masses, it looks like we're measuring relatively smaller spins. So maybe this could be telling us something a little bit interesting about the relative roles of accretion and mergers in different mass black holes. Another interesting thing to look at is the black hole spin and its relation to what we call the Eddington ratio, which is basically how bright this thing is relative to how bright we think it could possibly be. Turns out that there's not much of a relation there. There's quite a lot of scatter. Again, small sample size. It seems to be approximately constant so far. So the relation between mass, preliminary relation I should say, is maybe a little bit more intriguing than the relation to the Eddington ratio at this point. But that said, of course, there are a lot of systematic uncertainties that go into these measurements. As exciting as this is, we do have to keep these things in mind. We have to isolate the reflection from the absorption, the continuum, and the soft excess. We have to consider different degeneracies in the system. I haven't had a whole lot of time to talk about those, but if you have questions, please ask. If there's a jet in the system, that can introduce a lot of different X-ray emission into different parts of the spectrum and complicate things. And finally, we're also assuming that this ISCO, this innermost stable circular orbit of the disk, is literally the cutoff. You cannot go inside it and produce emission that meaningfully contributes to your X-ray spectrum. Turns out that if you do have a little bit of emission coming from in there, that can complicate things too, introducing systematic uncertainties into your measurements. But kind of moving in a tangential relation, at this point, black hole spin and jet production is another very active topic of research. And it kind of connects us back to this whole notion of feedback. So Blanford and Znyak, back in the late 70s, basically came up with a theoretical framework for this. You have a rotating black hole, you have a magnetic field threading the accretion disk, and when you combine those two things, you can get these outflowing magnetic field lines, these helical field lines, that carry out huge amounts of matter and energy. So this is a nice idea, but the specifics are still a little bit vague and unknown, how this actually works in reality, and it's an active topic of study. So we think, at the moment, that there might be the first hints of an observational correlation between spin and jet power in microquasars being these stellar mass black holes that have jets. So again, this is work that's actually being done here locally at the CfA by Ramesh Narayan, Jeff McClintock, and Jack Steiner. So it looks like there's the first hints of a correlation. I mean, only 5 data points, again, keep that in mind. But it would be very intriguing if this holds up. And it would be especially intriguing if this type of behavior holds up in AGN as opposed to microquasars, because this would give us an independent line of measuring black hole spins, at least in jetted sources. So these jets that we see in AGN and in microquasars seem to turn on and off over time. Of course, there's shorter time scales if you have smaller black holes. The AGN seem to turn on and off maybe over hundreds of billions of years. So the interesting thing to consider there is that spin itself only changes over very, very long time scales. You can only change the spin of a black hole on the time scale that would take to appreciably change its mass, at least a first order. So the question here is, what is changing that's causing these jets to turn on and off? Is it the accretion rate? Is it the magnetic field? We don't know. These are active questions. But the inner disk in AGN seems to be disrupted during the onset of jet production. So there have been some tantalizing hints there in some of the radio-loud AGN that we've looked at. And what I want to show you here is the Perseus cluster. This is one of the most massive gravitationally bound objects in the universe. It's a population of, I think, thousands of galaxies in this cluster. It's absolutely enormous. And when you look down at its core, there was one very big active galaxy, NGC 1275. And that's been extensively studied in pretty much every wavelength at this point. But looking at the X-ray and the radio studies have been some of the most interesting. When you look at density contours of the gas in the source, you see these characteristic ripples that form here. And when you do a technique called unsharp masking, they pop out even more. So this is work by a colleague of mine, Andy Fabian, and what he inferred from these results was that the jets are basically turning on and off over very long time scales in this source. When they turn on, they push out huge amounts of material, huge amounts of gas gets pushed, creating shock fronts and all sorts of things that are interesting. But ultimately, you get these characteristic compressions and rarefactions in the gas, the intercluster medium gas surrounding this galaxy. So it's basically like dropping a stone in a pond. You see these ripples kind of going out as the jets turn on and off and on and off. And you can actually take a frequency. I believe the frequency of this was B flat when you do that, if you translate it to sound waves. So that's interesting. And this is also really cool evidence that perhaps the energy being carried out by these astrophysical jets that creates these ripples in the space here in the intercluster medium is throwing out a huge amount of energy. What happens to all that energy? Where does it go? Well, when we consider our M-sigma relation again, in the context of all that we've seen from the black holes and the spins and the jets, and all that matter and energy that's being thrown out into these galaxies and these intercluster mediums, we start to think about this in a little bit of a different way. And maybe the thing that's driving this M-sigma relation is the so-called feedback that these jets are putting out into the intercluster medium. So the jets are throwing off matter, they're throwing off energy, and they're giving a huge amount of heat to all that gas that's sitting there. By heating up the gas, they're effectively halting star formation, because how do you form stars? You have to have a reservoir of cold, collapsing gas. Gas can't get cold and collapse if there's a lot of heat that's being pumped into it constantly. So basically, you have black hole sitting there, it accretes material, it starts throwing off these jets, maybe they turn on and off as the accretion rate or the magnetic field changes over long time scales, but they throw off a huge amount of heat, ultimately, into the ambient medium. And that heat prevents the gas and the dust from collapsing and forming further stars. So the black hole actually regulates the size of the galaxy, the host galaxy, in which it resides, in a very fundamental way. So it's interesting to think that black hole spin, which plays some very fundamental and as yet a bit unknown role in jet production, actually has influences that extend out to even megaparsec scales in these huge galaxies and galaxy clusters. It's a very fundamental property that seems to really shape the evolution of galaxies and the black holes in which they reside. So just to leave you guys with a few takeaway points, I just wanted to remind you that black holes are very simple. They're defined by their mass and spin. Spin is something that we measure by observing the gas orbiting the black hole in the innermost accretion disk and by reflection modeling. We've got about 25 supermassive black hole spins that we've measured so far, and they seem to indicate that the relative distribution is towards very high prograde spins. However, large grain of salt, small sample size. Also, we're looking at the brightest AGN because we need huge numbers of photons to do this. But what we can say is that ultimately, we would like to get a reservoir of, say, hundreds or even thousands of AGN spin measurements, so we can really start commenting on the distribution of spins, at least locally, in the universe. We know that spin can influence phenomena as many as 10 orders of magnitude farther away than the radius of the event horizon through these relativistic outflows or jets. and that the jets likely provide the matter and energy necessary to halt star formation and regulate the size of the galaxies in which these black holes reside. So in terms of where we go from here, of course, we want to mitigate our systematic uncertainties and spin measurements. There are a lot of assumptions that we make in our modeling about disk density and ionization structure and thickness. We need to be able to isolate the reflection, of course, in these systems, and we need to be able to break modeling degeneracies by having a lot of sensitivity, broad X-ray bandpass, high spectral resolution. Ultimately, we'd like to figure out whether spin is correlated with other properties of these systems like mass, accretion rate, host galaxy morphology, host star formation rate, radio loudness. We really suffer from a dearth of radio loud galaxies in which we've been able to make spin measurements so far. And ultimately, we'd like to probe out farther into redshift space and understand how or if the relations that we see above evolve with redshift as you go further back in cosmic time. Of course, to do this, we need instruments, and right now, the United States is in a position where we're trying to figure out what to do with the next so-called decadal survey. So every 10 years, the astronomy community gets together and kind of comes up with a big list of priorities to hand to NASA headquarters and say, here's what we want to do in the next decade. Now, of course, you have different communities, exoplanets, solar physics, people who study black holes and all of their wavelengths, clamoring for money, and it's a very limited pot of money. So we need to prioritize the things that we would like to do, and each community tries to put its best foot forward in terms of saying, here are the missions we would like to fly. So in terms of things to consider, making those prioritized lists, in order to do black hole spin science, we need missions with high effective area. We need big light buckets to collect a lot of photons, because the longer you have to point at things in order to do your science, the harder it is to do your science. We also need instruments that have good spectral resolution to help us break degeneracies between different models. We need a large X-ray bandpass, as NuSTAR has showed us. Looking in the high energies is just as important as looking in the lower energies. You need a holistic picture of these creatures. And finally, especially as we probe out to larger redshift, we really need to see instruments with high spatial resolution. So instruments with Chandra-like half an arc second resolution are what we're going to need in order to avoid source confusion as we go out to higher redshifts. So all of these things, hopefully, will get folded into the picture at some point. Unfortunately, the missions that we produce, as you know, sort of have a long lag time. So they gestate for a while before we fly them. So even if the community decides in the next couple of years that we want to build some enormous honking X-ray observatory that costs $1 billion, which, by the way, is not likely, but if we do, it probably won't fly until you are in your mid-careers if you go along with this. The good news is that we do have a lot of smaller missions like NuSTAR. That's an excellent example of what's called a SMEX mission that can come along and do parts of this science for very low cost. So it may be that the future, as we see it, is going to be informed by a lot of different smaller observatories flying and trying to coordinate with each other. It's something to keep in mind. Thank you. That is an excellent question. In theory, yes, the size of the disk should have something to do with black hole mass. The size of the torus, I think, is something that's still a bit of an open question. So Jonathan or Annetta can correct me if I'm wrong. Maybe they know more about this than I do. But as far as I know, we have no clue.
Because we don't, we don't really know what makes the torus.
That's true.
Right?
The torus,
Is it the galaxy,
yeah.
or is it the black hole?
Exactly.
If it's the black hole, it's the scale of the black hole, but if it's just ISM in the galaxy, then it's that.
Yeah. Yeah. And the other thing to keep in mind is that a lot of these sources, for example, our own Milky Way, don't have a proper accretion disk as we would like to think of them because they don't accrete at a very rapid rate, which is good for us and continued life on this planet, but is maybe not so good in terms of studying the black hole at the center of our own galaxy in some respects. So in that case, we have more of a spherical bonding type accretion. But yes, by nature, when I talk about selection bias, we're looking at bright black holes that are actively accreting. So the assumption here is that they all have these sort of prototypical thin disks.
Let's get for Ryan.
Okay.
how frequent are these jets? Do they always happen when some matter gets sucked into the hole, or is it something that's rare?
Well, the latest figure I heard was that jetted AGN are about 10% of the population as a whole. So not totally rare, but certainly not the most common either. How exactly they're triggered and why they're triggered in some galaxies and not others is another topic of active research. That's a really good question, and we don't have a really good answer yet. We know they have something to do with it.
There's one up there.
So is it, the jets that we've observed, are they regularly periodic? And secondly, have there been any kind of simulations to look into it and seen if we just take the assumption that we turn off and on the magnetic field, or not turn off and on the magnetic field, but can we replicate these events?
There have been lots and lots of numerical simulations of jets. This is a very, very active topic of research, and it's evolving all the time. Again, if you have the opportunity, Ramesh Narayan is a really good person to talk to about some of this stuff here at the CfA. He's done a lot of simulation work in this field. Interestingly, it's the microquasars that inform most of our knowledge about jets and their relative periodicity or lack thereof these days. Simply because the time scale for a jet to turn on and off on a microquasar is observable on human lifespans. Whereas for AGN, obviously it's not. We're seeing a snapshot of this thing over cosmic time. So there's been a lot of work done, both simulations and observations, showing microquasar jets turning on and off. And it appears that microquasars actually go through this kind of characteristic cycle. And there have been a lot of spectral and timing studies done showing exactly what the spectrum in X-rays looks like, depending on what period of the cycle this thing is in. So if the jet is on, if the jet is off, if the disk is sort of refilling. Recall that I said the disk is sort of disrupted during the onset of the jet event. So the disk seems to be refilling at certain times, and then it blows itself to bits when the jet goes off again, and then it kind of builds back up gradually, and then the whole thing starts all over again. There's been some really interesting work by Rob Fender. Also, if you're looking for references to reading papers and such, Rob Fender is a good one. He's done a lot of work on this. And also, of course, Jeff and Ramesh's group have done some very interesting work as well. So yeah, very active topic of research. Turns out that it's hard to specify an exact periodicity for AGN, simply because, like I said, we're seeing them on these very long time scales. So the ripples that we see in 1265 certainly seem to imply that these things go on and off. But there are a lot of other factors that come into play in trying to determine exactly what that time scale has been and if it's been regular or not.
I'll ask a different question from the one I was going to ask. That 10% of radio is 10% are currently on, right?
Yes, this is a good point.
And so actually, if there's a duty cycle of jet things, right, then it's a larger fraction of
Yes.
AGN that sometimes have jets.
Very good point.
And we
Absolutely.
don't, but on the other hand, we kind of, I think, those of us in the field sort of believe that not every quasar, so there are some quasars which never do jets, right? And so that's kind of interesting because I hadn't really thought that through. It kind of could be at the 50-50 level.
It could. I mean, it has to be, the duty cycle has to be at a certain level in order to pump out enough heat to halt the star formation and kind of make the M-signal relation work, right? If we're assuming that that's the cause. So we can kind of place constraints on it in that way. But you're absolutely right. I mean, we have to think of these things, you know, seeing objects like 1260, 1275, those ripples. There is some sort of duty cycle, and you can only observe the sources that are quote-unquote on at any given moment.
Right, so the question is, can we tell the difference between a radio AGN that's off and a true radio quiet AGN?
That's a really good,
Yes,
that's a good
because you
question.
have, radio plasma stays there for
Okay, because you've got the relic.
Yes,
You've got the relic.
relics.
Well,
The
but
relics. So this time scale.
so you think the relic lasts longer than the duty cycle?
Yes,
Okay.
because duty cycle is 10 to the 7 and relic 10 to the 8 and 10 to the 9. And maybe we don't really understand the relic, right?
Yeah,
Because
that's
you
what I'm
can have
worried
the
about.
expansion, you can have different magnetic fields.
I'm not convinced they all make relics.
Yeah, so it could be that you just get this less powerful jets, which are smaller within the galaxy, and they never expand to becoming a big radio
Now it's actually
structure,
true.
and that's possible because in radio quiet, that's what we had.
Yeah. There are definitely a lot of AGN out there that are radio quiet but not radio silent.
Yeah.
For example, my student Mason over there is working a lot on NT5151, doing some very excellent X-ray spectral work there, and that's a perfect example of a source that's radio quiet but not silent. There's definitely some extension there in the core that you see. So how much that could be influencing things is certainly a really good question. And again, that certainly argues in favor of having X-ray instruments that are capable of isolating the very central cores of these AGN, rather than just taking a big circle and extracting the spectrum of the whole thing. You probably have a lot of jet instrumentation in there. But having a high spatial resolution is very helpful.
Works for me.
Looks like that's about it. Join us next week where we'll be listening to Dr. Gonzalo Gonzalez Abad talking to us about exoplanetary atmospheres. So looking forward to that.
Let's have Laura here.